So looks like we're all here now, so we can begin. So in the previous session, you learned about what GPUs are and how the hardware works and how they're done. So today we'll start talking about how to program them using OpenMP. Just to start, few words. So I work here at the PCC University of Edinburgh, and so you can find here my email. So if you have any questions after the end of the talk, feel free to send an email and for any issue you might have, and we'll reply and have a look at that. So what we will be talking today is about using OpenMP to program GPU. So OpenMP, hopefully most of you have already some experience using OpenMP for CPU. In the OpenMP is a standard, so it defines a set of rules which then are implemented by compilers. Historically, OpenMP started for parallelizing work on CPU using different threads. However, in OpenMP 4 standards, so some basic support for executing code not only on CPU but also on GPU was introduced. And since then, all the following OpenMP standards have added new feature, which allows you more control over how to program your GPU using OpenMP. If you use OpenMP directives before, it's very similar. At the end of one of our last session will be covering OpenMP and the differences. But essentially, the main takeaway is both OpenMP and OpenMP do very similar things, although the syntax is a bit different. So the way you write the directives is different, but the directives mostly do the same thing. And they mostly map one-to-one, although not quite exactly. And it's still OpenMP, so you can use OpenMP to offload to GPU. You can also use all the other features that you know and love from OpenMP on CPU, like barrier reduction tasks and so on. And we'll see a bit how to use those more advanced tasks later on in the course. One of the nice features of OpenMP is that it's vendor agnostic. So no matter if you're using NVIDIA, hardware or HP hardware or Intel, OpenMP can work on all of these GPUs. So OpenMP asks to do some abstraction of the GPU. So OpenMP does not target only GPUs. It's meant to be a way to execute code on devices, on general devices that are not necessarily a CPU. That means you can also have multiple type of devices. So as far as OpenMP concerned, our device is some engine that can do computation. And as this unit, this engine, comes with some storage device as well. That means memory that is accessible on a device is not necessarily accessible from the CPU as well. So all of the data that you can use on the device comes in within a data environment. And on the device, you can use any data which is included in this environment. Whenever you want to execute some code on the device, you have to tell OpenMP that the following section need to execute on the device. And you can do so by using the target directive. You'll also have to, when you start your program, you likely have all your data is on the CPU and not on the device. So you also need a way to tell OpenMP or to transfer or map data which is on your CPU to the target device. So this is an example. So the way you do it as by adding a directive. So this is supported for both C/C++ and Fortran, although the syntax is slightly different. And it's the usual notation from OMP. So for C, it's a /pragma followed by OMP, and then the directive that you want to use. Because we want to execute some code on the device, we just add target. And in C++, then you add some curly braces, and anything inside the curly braces will run on the target device, on the device you're targeting. So similar notation in Fortran, but the pragmas are a bit different because the language has different rules. So it's a bang dollar OMP target. And because you don't use curly braces in Fortran to define scope, you also have to specify when the target section ends. Now, when we do this, we're telling OpenMP, please run my code on the device, so on my GPU. Unfortunately, we haven't told it how to spread the work across all the cores on the GPU. So OpenMP does not know how to spread the work, so it doesn't. So by default, what will happen is whatever code you have inside the target region will execute on the device by using just one thread. So essentially, that means you'll only be using one core. It will work, but it will be extremely slow. So that's probably not what you want to do. So we've talked about how we run most things on the CPU. So in OpenMP lingo, and not just OpenMP, this is usually called a host. So the host is what loaded and run the program and will typically run on the CPU. The device that you're targeting is usually a GPU, but depending on the context can be something else, for instance, an FPGA. Most implementation of OpenMP only support GPU, but that might change in the future. And the data that you have on the host is not necessarily visible on the devices. So whatever data you have on the host that you have declared needs somehow to be mapped or transferred to the device. So one of the ways to do this is that you create a mapping between some region of memory on the host and some region of memory on the device. And then you take care, you trust OpenMP to take care of doing all the data movements. So copying data from the host and back to the device. However, always be careful that you, whenever you access your data, it has been properly mapped while you're running it. So make sure if you have some data declared on the host, make sure to map it to the device before you ever touch it on the device. Don't use data you don't have mapped. Now, OpenMP is kind. So by default, it will try to map and do all the data movements behind the hood for you. And at least from the 4.5 OpenMP standard, so by default, if you have some scalar variable, it will consider them to be first private. So essentially, it will create a private copy for each of the threads and will initialize it, which is what you want to do most of the time. For other variables, there's other default behaviors for mapping from the host to the device. Unfortunately, while it often does a good job, it doesn't always. So my advice will be, whenever you have some data, always make sure to map them explicitly between the host and the device. In order to do so, you can use the how do you actually do it? You have to use OpenMP clause, which is the map clause. So you have your pragma or MP as usual, followed by target, which essentially means this is something that involves the device, so the GPU, then added by map. So map means I need to do some mapping between the CPU and the GPU. You then have to tell it what type of mapping. So are you mapping data which is on the host to the device? So essentially transferring data from the CPU to the GPU. Or do you want to copy data from the GPU back to the CPU? Then in this case, you from. Sometimes you want that at the end of the target section, you want to, at the beginning, you want to transfer data from the host to the device, do your computation, and when you're finished, send it back to the device. And you can tell it to do so. You can use two different map directives, but you can also do it in on a shorthand by using to from map type. And in some cases, you want some scratch temporary data to be created on the GPU, but you don't actually want to, at least not at this stage, to copy data from the CPU. So for instance, some big temporary arrays, for instance. So in that case, you can use the alloc directive. So that will allocate memory on the GPU, but will not do any data transfer. And that's followed by double column and then a list of variables for which we're doing mapping. Okay. So here as an example, so you have, say, two arrays, B and C, and you're essentially summing them. So you're summing the two vectors, the two arrays, and then you sum over each resulting sum, and you do a reduction. So you accumulate the sum over all the elements. So we give it target, which means this will run on the device, and then we'll add the map directives, which will tell to move data from the host to the device. So B and C, we're reading it on the device. So we need to make sure that the data in B and C is available on the device. So in this case, we have to map data from the host to the device. So we use two, the map type, and then the variables such as B and C. We don't need the data back. Once we've done with arrays B and C, well, we're not touching them, we're not changing them. So we don't need to do any copy back to the host. Those arrays have not changed. However, there is something we have changed, which is the scalar variable sum. So we want to make sure that when we're finished, the value of sum is moved back from the GPU to the CPU, because that's the results we care about. We also want to make sure that sum is properly initialized. We don't want to start it with some random value, which means we also need to copy whatever is the initial value for sum, say 0, from the host to the target. So because we're transferring data both from the host to the device and back, then we use the map type to from. So you can see here two different notations. So the left is for C, C++, and the right one is for Fortran. So throughout the course, we will show examples both in C, C++, and for Fortran, which are the two languages which are officially supported by OpenMP. Okay, so I see there's a question. So on slide 11, will there be a race condition, or does to from by default ensure reduction? So it will be if this was actually running in parallel. So this, however, because we have not told it anything about how to spread the work between the different elements, actually this code is serial. It will run on the device. It will use just one core, one thread, and it's all serial. So there is no race condition because there's actually no parallelism here. Not yet. We'll talk about when the data is allocated and deallocated later on in the course. So Chris, hang on. The answer is coming. But we'll cover that later. Okay, so executing on this device is sequential. There is no parallelism whatsoever. Now, the whole point of using a GPU is to exploit parallelism. So we need to tell away OpenMP how to spread all these tasks, all these loop iterations across all the thread. Now, why does this happen? In part is because so you can use on the device all the OpenMP all of the OpenMP structure. The problem is the device is a bit more limited than the CPU. So on the CPU, when you have no matter how many threads you have, they can all communicate with each other, they can synchronize. Now, you've seen how the hardware is works for GPU in the previous session, and you covered how the GPUs are divided in streaming multiprocessor, according to NVIDIA terminology, or computing units in AMD terminology. I will mostly use AMD terminology because that's the GPUs we have on ARCHER2 at the moment. But they essentially always map one-to-one. So if your threads, if you're using threads spread, you can only synchronize across threads in the same computing unit. You cannot do any communication between threads on different computing units except for reading memory, for reading data from global memory. So that means you can't have bias, you can't have all of this construct. So that means you need some mechanism, some way to tell OpenMP to group some type of task and execute them on different streaming multiprocessor. Okay, so now so we have the same example as before, but this time we're trying to get it a bit more parallel. So you can see that here we are the parallel for. So when we tell it to be, so we use the usual parallel directive, which essentially means, okay, OpenMP, this is a parallel region. I want to execute things on the device and in parallel. I'm doing a reduction, so I want to avoid any data races, so I add the reduction, and the parallelism is over the loop. So I add parallel for. Analogous terminology for Fortran. So this will run in parallel, but because we can have any type of code, any synchronization inside the code, you will only be able to run on one compute unit. So you're running in parallel, but you're still not using the GPU. So you're using just one compute unit. So if I remember correctly, our GPU has 104, I think, compute units. So that's a really small fraction of your GPU, and the rest is wasted. So we need some way to tell it to run different tasks on different streaming multiprocessor, or whether that one cost will be more limited because we will be able to do synchronization inside one compute unit, but not across compute units. Okay, so we need something else to group threads inside one streaming multiprocessor. So we do this with a teams construct. So a team is a group of threads that can, from OpenMP perspective, can communicate with each other. So each team will have a master thread, which is similar to the master thread you have on a CPU. And then whenever you create a team, that will spawn multiple threads, additional threads. And these threads can use all the barrier and all the synchronization mechanism you know and love. You can also control the number of teams and to some extent the number of threads per team. So in this example, you can see we have first we use target, so run this on the device. Then we have to tell it to create different team. So we add the teams directory directive. Then we want to tell it, so all of these teams, we want them to distribute them across all the compute units. So don't put all your teams on the same compute units, spread them around the GPU. So to do that, we use distribute, And then we have to add it where the parallelism come, that it's parallel. Okay, so there is parallelism. So we add parallel, and that parallelism comes from the for loop. So we add for. And then there's the usual mapping, so to make sure that the data is on the is properly transferred from the host to the device. Add the reduction clause to make sure there is no rest condition on some. Okay, so finally, so we can do this. There is no synchronization whatsoever, except one. There is a form of synchronization going on here. Does anyone can tell what types of synchronization happen? So all the iterations are doing something independent. So summing two elements of vector. But what do they all share? Why do you think there is actually some hidden communication between threads and between teams? Yes, yes, correct. There is a reduction step. So all of them are reading and writing from the same variable. And you want to make sure that there is no, they're not overwriting each other. So that there's no rest condition. Now that's taken care from reduction. However, it turns out you can do a reduction without requiring that you can do a reduction using well, there's various ways to do it, but in the end, you can rely on atomic operations. So atomic operations protect the memory, but don't create actual synchronization at the software level. You just make sure if someone is writing to this variable, I'm not allowing anyone else to touch it. So that's done directly in the hardware from the memory. So that can be done between different streaming multiprocessor. So atomic operation do work across different teams. But that's about it. You can't have a barrier. That's the only form of, if you want, hidden synchronization that you can have. So basically, communicating from memory. Well done. Okay, so essentially this is what's happening. So you have all your loop, and you have various. The loop is iterating between 1 and n. And what you want to do is that, okay, I'm going to break this loop in smaller loops. And then, so smaller section of a loop iteration. And each one of them, I'm assigning to a team. So in this case, we have 4 teams. So the first team takes the first n divided by 4 elements. Then the second team takes the following chunk of n divided by 4 elements in the loop, and so on, until we cover all of them. So those are teams, and the teams can go, well, anywhere, but they can be, what you know is that all the teams will go on the same streaming multiprocessor or compute unit. That's because while you can't have synchronization between teams, you can have synchronization between threads in a team. So first create all the teams, and then create the threads inside the team, send wool into computing units, and they can happily communicate with each other inside the team. There are some hardware limits on the number of teams that you can send at the same time on a GPU. So essentially, it's because each team goes to a different computing units, they have to fit on the device. So if you have too many teams, they won't be able to run at the same time. But we'll cover this more performance aspect later on in the course. There's also some restriction on the number of threads. That's because the threads generally map to actual hardware threads in the GPU, which you've discussed about in the previous section. And there are only so many threads you can run at the same time in a streaming multiprocessor. Okay? So what you typically want to do is to have a target, run the device, teams, generate teams, distribute, spread them across the compute units, parallel. So this spread run the execution in parallel, and then parallel do, just to give a Fortran example for once, and those parallelism is in the do loop. So that will generate the teams and the threads inside the team. And if you're lucky, you might be using the whole GPU this time. So if you're familiar with OpenMP, you've probably seen that on the CPU works with a fork join model. So you start on the CPU outside of the OpenMP region, running on a master thread, and then you enter a parallel region, and then you fork and create all the threads. And when your parallel region is finished, then you join all the threads together on the master thread. Now, logically, the same thing happens here. So whenever you create the difference from what you probably will do on the CPU is that on the CPU, you typically don't use teams. You can. Teams are not anything new in OpenMP. You can use teams also for CPU, but you rarely do. They're rarely useful, while they're essential when writing to a GPU. So you first fork the teams, and then inside the team, you fork the various threads, and then you join. That's all actually, that's how that's the view of the world of OpenMP. Now, that doesn't always match to the hardware, because actually in the hardware, all the threads are will be running anyway. So in reality, you often end up with lots of threads that start at the same time, but they're all doing nothing. They're basically stuck in a loop until the first threads tell them to wake up. But that's up to the implementation. Depending on how the compiler wants to implement this fork join model on the device. Okay, so you can use the you can tell it how to schedule the how to distribute the teams. So how essentially how big are the chunks of iteration. So this is similar to other distribution clauses you might have seen in OpenMP. So in this case, we're telling it to group in chunks of 4. So yeah, it's essentially the same as the schedule clause on work sharing loops that you might have seen on CPU. So you group all your interaction chunks of a static size, and then you assign them to teams in round-robin way. You have some control to specify your iteration per chunk. The default is usually okay. Okay, so you can use, we've told how we can use synchronization. You can use all the barrier, critical regions, and so on that you know and love. But remember, why within a team, not outside of a team? Which means you're a bit more constrained on the CPU, where you are often, it's enough to have just one team, the default one. Atomic constraints, because they protect the memory, can be issued from any team. So it's safe to use atomics also inside teams, even if there's different teams touch the same memory location. And so you can call function inside a target region so that your code can be properly organized. Or whether you sometimes have to tell it, you have to tell OpenMP that the function can run on the device as well. That's not always necessary, but it typically is if the function is defined in a different compilation unit. Essentially, when the compiler finds wants to encounter the call to my func, to your function, it needs to know about it. It needs to know, and while you tell it about that function exists somewhere and you want it to be on the GPU, is by declaring it. So you have to add the declare target, and then you can use it on the GPU. So yes, essentially atomic is the only back of the way to synchronize across teams. Okay. So this is the same example in Fortran. So using a slightly different syntax. So you can query information about your environment. So you often have multiple GPUs, so often 4 or 8, depending on hardware. So you might want to have your program checks. Okay, how many GPUs can I use? You might want to select which GPU you actually want to offload code to. You might want to offload different section of your code to different GPUs. So OpenMP is mostly directives, but it also has function calls. So these are examples of some of the function you can use to query some of essentially hardware information, like what is the maximum number of threads of teams that I can submit, or the maximum number of threads, and also information like if you're running on the device and you ask yourself how many teams do I have, you can use OMP get num teams. Or if you want to tell OpenMP from now on just use this number of teams, you can use OMP set num teams call. So many of these have an equivalent in terms of directives, but not all of them. And some of them only make sense on the device, others only on the host, and others in both. Okay, so this is an example which is fairly common, which is you have some MPI program. So you launch a problem with multiple ranks. So you essentially have multiple copies of the same program running, and you want each copy to use a different GPUs. So what you can do is to call mp get num devices, and you know how many GPUs are, and then you set the device in a round robin fashion. So each rank will get a different GPU. And this is some example in Fortran. Yeah. So one way to control a number of teams and limits on the number of threads is by using the num teams clause. So you can tell it exactly how many teams you want, which means you can tune it to whatever hardware you have. And you can also set a maximum number of threads. Essentially, you can control how big those teams are. Note that you can't exactly tell it the number of threads. That's because hardware may have restrictions on how many threads at the same time. For instance, on NVIDIA, there will need to be a multiple of 32, 64 on AMD. So there are limits. So what you can tell we can tell it is the maximum number of threads. Okay, so so this is the some example using Fortran, and here as well you can use directives, or you can use the function calls, or well, function subroutines. So you may have noticed that even to parallelize a very simple loop, it's quite a long series. You have to do a OpenMP target, teams, distribute, parallel for, and then all the mapping. So again, even for simple example, there's quite a lot to write. So if you're on a lazy mood, what you can use is to shorten it and use target teams loop. So this means use the device, use different teams, and the parallelism is in the loop, so on for, and figure it out. Figure it out how to assign threads, how many teams, how many threads, how to do the mapping, and so on. This often works, but not always. So essentially, you're telling the compiler to figure it out, and the compiler will try its best. And sometimes it does a very good job, and sometimes it does a very bad job. And how good the job is done will depend on your hardware, essentially, and your compiler. Okay, so it's a bit of a gamble. It might work, it might not work. It's also useful to get some information as well, especially at the beginning, to ask questions like, am I actually using the GPU? It's running, it's giving the exact result, but I'm actually offloading to GPU. Am I using all the threads? Is the data being moved around? So there are various ways to look at it. So there's essentially two directions. One is to give them some compiler flags. So they're compiler specific, and they'll give you, when you compile, it will give you some information about what the compiler is doing. So this is an example for the NVIDIA compiler. So you can use this minfo equal mp, and at compile time it will give you well, a lot of information about what it's doing, often more than you need. Okay. So this covers a bit of our first walkthrough of our parallelism work on a GPU using OpenMP. So here you can find a link to the latest standard, which is version 6. Note that this is the standard that is supported by your compiler is probably older than that. So this came out quite recently. So if you're using an older compiler, it probably won't support all the features of OpenMP6. So you can, if you, the OpenMP specification is quite complex, so it's very hard to understand. However, they also have some examples, so that's very useful, especially when you get started, to see how to use some of these features. Just be aware that some of those features might not actually be supported by your compiler. So most compiler will have a list somewhere of which features they support or not from a certain OpenMP standard. Are there any more questions or doubts, perplexity at this point? Anything unclear or any random curiosity?
Hi.
Hello?
Can you submit a job and see, show a sample script or a package just to see OpenMP is working?
I'm sorry, I'm not sure I understand the question. So you're saying...
Can you submit a SPatch script or a job in ARCHER2 for a sample OpenMP? Like
an
a script?
example.
Yep.
I'll talk about that right next to it. So we have some examples for ARCHER2, yes, and
Okay.
I'll cover that right after.
Right. Thank you.
Any more questions? Okay. So if you go on the ARCHER2 webpage on the course, you'll find a link to the materials, which is this ARCHER2 GPU directives GitHub repository. So it's public, so anyone can see it. And you can see we have a few exercises that I propose you can have a look. So we have so the one for this section for what we covers what we covered today is the SPY instructions. So this is a very simple program that wants to compute pi. So so the number pi is using a Monte Carlo mechanism. So we have instruction on how to so essentially an exercise how to port this really simple code from CPU to GPU, making sure that you do some mapping, very minimal mapping, and also distribute. So my proposal is that you follow the instructions and have a go at parallelizing it. And don't worry, we'll go over this later on at the end of the course. So all of these exercises will go over them together later on. Although we won't do this today. Okay. Any questions about both exercises? So you'll find all the instructions there, but if you have any obvious problems with that, just let me know. Okay. So next, what we'll talk about is data movements and how to move data. We'll talk a bit more in depth how to move data between CPUs and GPUs. So I suggest we have a very short break. And we reconvene in 5 minutes, just time for people to take some tea or just have a walk. Sounds good? Perfect. So I'll see you at 11 in 5 minutes. Hello. Hopefully everyone's back. So we will now talk more in details about something we've already talked about, which is how to move data around between host and the device, and hopefully answer some of the questions that were posed before. Okay, so this is a bit what we'll just very fast recap about what we've covered before. We'll talk more in details about the map directives and also some other ways to manage data on the GPU more efficiently using data directives, which allow you to manipulate the environment, your data environment, which we talked about at the beginning of the previous lecture. And so we'll give a few suggestions on how to handle all this memory transfer, and give some more details about OpenMP keeps track on what data is on the CPU, what is on the GPU, and how it manages it all. And we'll also hint to what unified memory is, which is a way for GPU and CPU to access the same data. And finally, a few tips and tricks along the way. Okay, so we've seen so data is different depending whatever you are on the host or on one of the device. So a device has its own memory space. So the host is essentially the CPU. So that's where a normal program without any support for GPU normally runs. It's where I would say most programs always start. So you have a C, C++, Fortran that's going to be loaded on the CPU. And typically what you'll do is that you'll initialize your data or reading data files from storage, and you'll end up with some data on the CPU, and you won't be able to use it straight away on the GPU because they're not accessible. So the GPU has its own device memory. It has a global memory, which means the memory can be accessed by any team and any threads. So we told before, oh, they cannot synchronize, but they can all access. They can all access the the same underlying memory. Just make sure you to protect your data access with atomic directives if different threads are accessing the same type of data, the same memory location. So when you run something on GPU, so when you submit a team that launches, essentially that creates something called a kernel, and it launches on the GPU. The kernel will only be able to usually access the memory on the device. Now, there is a way for the device to use memory which is on the host. So that feature is usually called unified memory, and it means that it allows any kernel, any code that executes on the device to access data on the CPU without doing any of the memory mapping we've talked about. Most recent GPUs do have some support for unified memory, which means it will work, but does not mean it will work well. So on many GPUs, the interconnect between between the GPU and the CPU is really slow. So that means if you use the unified memory, which will essentially shuffle data around under the hood for you, but across a very slow interconnect, so it will be extremely slow. The exception is some newer models of GPU, which instead have a very fast interconnect between the CPU and the GPU, or in the case of the MI 300A from AMD, they actually use the same memory. So both the CPU and the GPU access the same memory. While on the NVIDIA equivalent, so the Grace Hopper, they instead, what you have is that there's different memory for the CPU and GPU, but the GPU can access relatively fast the data which is on the CPU and vice versa. So if you can use one of the CPUs, you essentially don't need to bother as much for data mapping. It will work with acceptable performance, although maybe not the maximum performance, as you still want to access the data that is nearest to the device you're using. So these type of devices, you can find them, for instance, in Europe, in Jupyter, which is a new exascale machine. And in the case, Embed AI is a large system with Grace Hoppers, although that's only used for AI workloads. So the main takeaway here is you have to take care of data movement, and that's very important, especially if you want your GPU to work well. As in, you ideally want, if you're making all the work of offloading to GPU, you probably want it to be faster than running just on the CPU. So if you want to acceptable performance, you have to take care of data movements, because the data movement is slow between CPU and GPU. That's because the interconnect is very slow interconnect compared to the type of interconnect you have between different cores on a GPU. So OpenMP tries to be clever. And so it will try to, as we said before, it will try to do the right thing. But generally speaking, it might fail, and we'll see some example where it fails to do the right thing, which means your program will expect data to be on the GPU, but it isn't. The other reason you want to control when the data is being done is because if you let it happen by default, OpenMP will be quite aggressive. Essentially maps everything from the host to the device at the beginning, and then when you're down in a kernel, map it back from the GPU to the CPU. Now, sometimes that's what you want, but not always. For instance, suppose you're doing some type of fluid simulation, and at each step you're computing what is the density of the fluid at the next step. But you don't need the data in between. You're doing a lot of steps, and on each step you just need the old data, which is also on the GPU, and then generate new data on the GPU. So whenever your kernel that compute the new time step finishes, there's no need to move the data back to the CPU. You don't need all the time steps. You just need a few of them. So that's one case where you really don't want to keep transferring data between CPU and GPU when you're not using it on the CPU at all. So this is done with the map directive, so following the map clause actually, following the target directive. So my advice is always to map everything. So it's a bit similar to the advice you often get when you first learn about OpenMP, of always declaring all your arrays, whatever they're shared or private, all of your data, because by default everything is in shared, and then you end up with race conditions you didn't expect. So here it's similar. It's safer to map everything. Okay, so we've seen this syntax before. You can map data to the GPU. You can map data from the GPU to the CPU, or you can do both. So map data from the CPU to the GPU at the beginning of a parallel section on the device, and then at the end of the parallel section, you copy back all the data on the GPU, which will have changed, to the host. Okay, and okay, this is what it look like. OpenMP target teams distribute parallel for all the parallelism, and then the mapping for the array. Okay, so similar syntax in C and Fortran. Now, here is something to be careful of, mostly in C++, which is I said that it tries to do the right thing, but the compiler doesn't always. Now, if you're using some static array in C, which in real-world applications are very common, then the compiler will know your arrays, how big they are. So in this case, for instance, you have some static array of size n, and you have arrays A, B, and C, and then you want to map it to the device, okay, and you can just give them the name of the variables. Now that's fine because the compiler knows how big the array is at compile time, because they're static arrays. So it can figure out, okay, this is an array, and this is how big it is. So I know which regions of memory to transfer move between the CPU and the GPU. However, if it's a dynamically allocated array, which means at compile time you don't know how big it is, you only know that once you actually run the program, which in C it will typically be done with alloc. If you're using C++, it will be new. So when the compiler sees this, it has no idea how big the array is. There is in C, there is no information associated with the variable A about the size. So this is, let's call it feature of C++, which doesn't really know that there are arrays. All they know about is that A, B, and C are pointers to memory location. There is no information whatsoever about the fact that they're actually arrays and there's a certain number of elements which are allocated. So in this case, you have to tell map, you have to tell OpenMP how big these arrays are. So the way you do it is by adding square brackets, and inside this, yes, is this the same with vectors? Not sure what you mean by vectors, but essentially yes. So it's if you mean a one-dimensional sequence of elements, then yes. C programming language don't really have a vector is more a mathematical concept, more of a programming language concept. Not sure if that's what you mean, Toro. So the first element inside the square bracket is the index of the first element in the array that you're pointing to, and the you have to this is followed by a double column and then the number of elements. So Sean is asking, does it support STL, which I expect means the standard library? So can you use it with std vector and so on? So you can use it with both, although sometimes you have to use it a bit lower level. So the way I typically do it is with passing the essentially you have your STL vector. Oh, now I understand what you meant by vector. Yeah, sorry, Tower, I misunderstood. So if you pass a vector from the standard library, call .data on it, and that will essentially give them the array, the pointer to the data, and then just use the 0 and. So I should double check whatever you can try to give it a std vector. I don't think it will work, but I will need to check. I'll double check. Let you know whatever it works right out of the way. So that I'm not sure. I don't think it does, but I'm not entirely sure. Okay. So you have to map to so in this case you're mapping the array B and C from the host to the device, and then you're mapping back to the host the array A. So this is full example with a parallel loop. Now this is one of the cases which is probably not the most efficient way to write it. So you can see that here I have first a loop, then I have a second loop. So the first loop is reading from arrays B and C, and saves the result to another array A. You also have a second loop, which is again reading from B and C and writing to some other array D. So in this case, we want B and C to be available on the device. So we shall map to B and C. And we want the results back. So you have a map from A on the top loop. Now, if you look at the below loop, similar, we still want B and C on the device. And we want to get data from D back. However, we already moved B and C to the device in the first loop. And we haven't changed the data in between. We haven't written to B and C. However, if you write it like this, what will happen is that first we transfer B and C from the host to the device, and then we do it again. So ideally, what we lack a way for the arrays to stick around on the GPU so that it can be reused again from the second loop. And this is essentially some example with Fortran. Okay, so the way we do we get around this is using structured data regions. So we have a OpenMP target, which means, okay, this section is about GPU, but then we add data. So this means, okay, we want stuff on the GPU, but this time we don't want to do execution on the GPU. Instead, we want to do some data operations, data transfer operations between the CPU and the GPU. So data is following by which data operations you want to do. So in this case, we want to transfer data from B and C from the host to the device, but only once. So we do map to B and C, and then we create this data region, which is whatever is between the top and bottom curly braces. Now, everything inside will not run on the GPU. Okay, we're still running on the CPU. However, once we're inside the parallel region, we know that the data has been transferred from the host to the GPU. So that has already happened. So now we have a 2 for loop, and we can submit them to the GPU in the usual way with a long target teams distribute parallel for the active. But at this point, we know that B and C are already on the GPU. And because we're inside this data structure, we can safely use them. So there's no need to map again inside the kernel. So inside the directives above the parallel loop. So both loop A and loop B, no need to map B and C. We still need to map back the results, so A and D. Okay. So in this way, we get that the data is transferred only once when we enter the data regions, and we keep it there. So any following parallel loop on the device can use the data. Okay. Same example in Fortran, so using very so similar syntax but slightly tweaked for the Fortran case. Okay, so how does OpenMP actually keeps track of all these memory transfers, all this data on the CPU mapped to data on the GPU? So we've seen this, the way it does this is by implementing some referencing counting. So essentially is every time it encounters a map directives, it will map between the, say, between the GPU and between the CPU and the GPU, so possibly doing a data transfer. However, what if we call map again on the same data? The data is already there. So do we actually need to do a copy? So by default, this doesn't happen. So if you call map again, if you call map on map to say on vector A, on array A, and then you do it again, it may ignore you. And okay, the data is on the device, so I'm not going to touch it. However, you can tell it to change this behavior. So this can happen. For instance, suppose in the previous example, we move data from the CPU to the GPU, but then we modified on the CPU, and we want to make sure that the GPU copy is up to date. Then we want to map it again, despite the data being there already. So we can tell it to use the always modifier in the map clause, so that the copy is always done. So we override this behavior. Okay, the way it's implemented is every time you encounter a map2, so it keeps track of how many mapping we made for that variable. So every map2, you increase the counter by 1, and every map from, you decrease it by 1. Whenever the reference counter gets to 0, then it means we no longer need the data on the GPU, so you can deallocate. So there was a question about this before. So does it deallocate at the end of the parallel region? So in the example we had before, if I remember correctly, we had a map2 at the beginning, or essentially a map2 at the beginning of the parallel region, and then a map from at the end of the parallel region. So assuming there is we're not inside a data region, a target data region, then that means that the data was mapped once at the entry of the kernel. So reference counter increased by 1, and then decreased by 1 at the end of the parallel region. So then it got deallocated. So the answer to the previous question was yes, data gets deallocated. That's assuming you have called on that variable the same number of map2 and map from, including the ones that are auto-generated by OpenMP. So by default, if you don't tell it which map it is, it will create its own map, which is part of the reason it's always better to use mapping. So you have a better understanding of what's actually on the CPU and what's on the GPU. Yeah. So why is this useful? Because the behaviors of to, from, and to, from change depending on what the reference counter is. So if the reference counter is greater than 0, then it's already on the GPU. So there's no need to copy data around again, so it won't do it. The only thing it will actually do is to check the array sizes. So the one in the square bracket, so it will check that everything is consistent. If it isn't, it will throw an error. So it does some sanity checks, but it won't actually transfer data. Sometimes that's not what you want to do. Sometimes you always want to transfer data, no matter if it's on the CPU or not. If you have some data you have mapped without always, and you want to you have it on the GPU, but you want to transfer again data from the CPU to the GPU, maybe because it's changed on the CPU, then you can do target update command, which essentially will always do a data transfer. Okay. So whenever the reference counter gets to 0, memory is deallocated on the device and it's gone forever. Okay, so here is, if you want some example. So in this example we have target data region where we're mapping the B and C arrays to the GPU, and then we call some function. So essentially, we have some code that takes care of where the data is, which is the target data directive. Then we have some other function which is responsible for doing some operation B and C. Now, we want to avoid duplication of code. So for instance, in general, we might want to call this function from other regions in the code where there's no data regions. So in general, if we want to make this function work everywhere, we make sure that we do the mapping. So we have to repeat the mapping to um, B and C inside the kernels. That's because we don't know where this function is called from. It could be called from inside that region, it could be from outside the region, and we want to make sure it always works. So if we run it inside that data region, so outside the data region, then whenever we enter the first for loop, there's not been any mapping before, so the reference counter will increase by 1. And then there's an implied map from at the end. So then the reference counter becomes 0 and the data is moved. Or if you put it in a data region, then the data is already on the GPU. So the data transfer will not happen. Okay, so this way you can have a function that always works, will do the data transfer when it's needed. So that's the reason for all this keeping track of how many times data is being mapped, is to avoid unnecessary copies, but still make sure you can write your code in a modular way without caring too much about what your data environment is. And okay, this some example with Fortran. So different syntax, but essentially the same. Okay, so we have seen to, from, and to, from before. Here we are showing instead the alloc directive. So essentially, this will will essentially do a mapping between some CPU and GPU for a variable, but will not do any transfer. It will allocate the data on the GPU, but not do any transfer. So that can make sense if, for instance, you have some data that doesn't need to be initialized. Or you want it to initialize it on the GPU. So there's no point in doing any data transfer. Map release, what it will do is essentially it decreases the reference counter by 1. And if the reference counter happens to be becomes 0, then it will deallocate it. If you've mapped multiple times the device, the reference counter will not become 0 when you call map release, so it will not be deallocated. Now, sometimes you want to tell it, okay, I don't care how many times I've mapped it, I no longer need the data, just delete it, remove it. So you can tell it by using delete. So this will essentially set the reference counter to 0, and then OpenMP will take care of deallocating all the data. Okay, so the other special modifier that we've seen were always. So this essentially, you can add it, essentially says you always make the data transfers, even if the data is already present, which means the reference count is greater than 1. Close it's really just a hint and on where to allocate the data. So OpenMP will allocate the data on the device, but you don't tell it where exactly to allocate it. So there might be different memory spaces where you can allocate it. So OpenMP tries to be as hardware agnostic as possible. So it does the concept that there might be different memories, and this is a hint that you give to a compiler. Please allocate it on a memory which is close to the device. So this, for instance, can make sense for unified memory, where data can be accessed both from the CPU and from you have some memory which is close to the CPU and close to the GPU, but can be accessed from either of them. Or whether one is accessing data from the GPU is faster if you use the memory which is on the same packet as where the GPU is, compared to the memory which is attached to the CPU, because the interconnect is lower. So in that case, the compiler might do something smart and allocate the data directly on the memory attached on the same packet as the GPU, compared to the one that is attached to the CPU. You're not given any guarantee. This is just a hint. So the compiler might ignore you, and that's actually what most compilers do because it's just not implemented. But it still follows the standard. So the standard doesn't say you have to do something, just say, please do it. So you're essentially telling people, please do something smart if you can. So we'll talk about mapper later on in the course, but this is a way essentially to organize together data transfer when your data is not just one array, but it's spread out across many arrays, or you have complex C++ data structures. And doing just straight mapping like the ones we've seen before will not work on this more complex type. Unfortunately, not all compilers support it. So I think the NVIDIA compiler still doesn't support it, but might be out of date on the most recent compiler. Are you sure one is also iterator? So essentially, this allows you, instead of mapping everything, you can, so a continuous, instead of mapping a continuous chunk of memory, you can say map all the even element or all the odd element. And it's a feature you can, that works on both C, C++, and Fortran with slightly different, with different syntax. Okay, so these are some examples of the one we've seen. So in this case, we have outer data region where we are allocating to arrays, so A and B. And at some point, we're on the GPU and we call OpenMP target update. So that means please do the data transfer. No, A and B is already there, but I still want to do a data transfer. Then you have to tell it in which direction. So you say to, which means it's going from the host to the device. And then you tell it which variable you're doing this for. And then you might want to do the same for the array B, so you want the same. So OpenMP target, it's on the device, update, do the data transfer. But this time, I want to do it in the opposite direction. So I'm transferring data from the array B to the array A. And okay, this is the same example, but in using Fortran syntax. You may have noticed my C bias, but the concepts are the same in both C++ and Fortran. And you can also tell it, so again, this is a feature, it's not always very well implemented in compiler, but you can also add if clauses. So essentially, you can tell it, okay, do the data transfer if this condition is true. For instance, suppose you're doing the flow simulation we were talking before, and we were simulating 1,000 time step, but we don't actually need the, to save the results from all the time steps. Because the time step is very small, but we only want to save every 100 of them. So what we could do is that every if a number of steps, say, is a multiple of 100, then transfer data from the GPU to the CPU. While for the rest of the time steps, don't do it. Just everything stays on the GPU. We're doing all computation on the GPU, so there is no need to transfer data back to the GPU. So data is already available, so you have to make sure to use update. If you want to transfer data back from the GPU to the CPU, it will be update from. We'll talk about no wait better later on, but for the moment, let's say so far, all the commands we've seen were blocking, which means once you enter the data region or the parallel region where we apply the map construct, you're guaranteed that the data is there. But sometimes you would like to overlap some computation, say on the CPU, for instance, with data transfer. Or you may overlap some data transfer and computation on different types of data, different data. So you can do that using no wait. So this is asynchronous. So the mapping will happen, but you're not guaranteed that it's finished. We'll talk about this in more detail later. Okay, so the regions we saw with these data regions where we could tell it whether there was data on or off. The problem is that if we want to, what we like is a way to tell it, okay, we want to write some function that submits all the data to the CPU and then do whatever. So call many functions or who knows whatever your complex code is doing. Now, that's a bit difficult to see with those structured data regions we've seen before. And that's because all the code needs to stay in the curly braces. Now, if you're writing a code from scratch, a simple code, that's fine. But if you're trying to port a complex code on the GPU, then your code is all over the place in many files. So it's difficult to wrap everything inside data regions. And you risk also to repeat yourself, which is something as a developer you hardly want to do. And it's also useful if you using object-oriented style of programming, while you have some object which is created and destroyed, and whenever that object is created, you may want to create some data on the GPU. Whenever your object is destroyed, remove them from the GPU. But you still want your object to be called from wherever in the code. So you can't warp everything into a data region. So hopefully there is a way to tell OpenMP, send data to the from the CPU, say, to the GPU, and keep it there. So no, so it will create a data environment, and it that would be valid for any following code. And the way you do it is with target enter data, followed by which transfer you want to do. So essentially using some map concepts. And if you want to tell it to get the data back, instead of enter data, you add exit data. Okay, so this is an example where we have some C++ struct which contains an array. So it's C, so it's a pointer to, this case, a double, so double precision. And in the constructor, so whenever we create an instance of this object, we allocate some memory. And what we want to do is to map it to the GPU as well, so we can use it straight away. Because we don't know where the object is created, we don't know which methods we're calling on this object, we can't wrap everything inside that target data region. So instead, what we tell it is, we tell OpenMP, okay, send it whenever we call this, when the object is constructed, map the data between the CPU and the GPU. And in this case, well, it's not initialized, so we don't need to actually do the data transfer. So we just use the alloc directive. And when we destroy this object, okay, we're done. We don't need a array anymore, so you're free to deallocate it. So we can use exit to say, okay, we want to do some synchronization between, we want to move some data from the GPU possibly to the host. Now in this case, we don't need to, because we don't need A anymore. We just want to deallocate it. So we use delete. If we actually wanted the data back, we could have used from instead. But we don't need that. We just want to delete to deallocate the data. There's finite amount of memory on the GPU, so we want to make sure that we don't waste it. So we call it delete, and then the variable is dynamically allocated, so make sure to specify the first element of the array and how many elements are in the array, which in this case is just n. And okay, this is the same in Fortran. Text to slide because it's Fortran, and you do have objects in Fortran, but they are slightly a bit more variables. But essentially, is the same concept where you're allocating, deallocating some dynamic array, and you use the corresponding instructions for mapping the data between CPU and GPU. Okay, unified memory, we have touched upon, we've hinted about this, we'll repeat it here. So it's not always necessary to do all the data transfer. You can tell OpenMP, if supported by the device, to use unified memory. So no need to do the data mapping, you can just use the data which is on the CPU. So this will work on most GPU, but it will, on most GPUs, it will be really, really, really slow. So it's not usually something you want to do, unless you have a GPU with a very fast interconnect between the CPU and the GPU. So between the memory on the CPU and the GPU, like in the Grasshopper, or in the case where they're actually both CPU and GPU accessing the same memory, so the same memory chip, which is what happens in the MI300A from AMD. So these are a bit more rare, more expensive devices, so you don't always have access to them. But it is an option if your code is very complex and it's very difficult to manage all the data transfer. It's often one of the biggest difficulty when importing data. So there are various ways to turn on unified memory. Usually by default it isn't. So by default, if you try to access data on the CPU from the GPU, well, your application is just going to crash. So you want to somehow make sure that if you're accessing memory from the CPU, unified memory is actually turned on, assuming it's supported. So the way you do it in OpenMP is using this requires directive. So essentially, you have at the top of each subroutine, you have to add this OpenMP requires unified shared memory. This is the OpenMP way to do it. There are other ways, which are vendor specific, often by setting some environment variable. For instance, My300A, you can set an environment variable that will turn on unified shared memory, no matter whatever you have. This requires unified shared memory or not. But this is the standard way to do it. So all devices will which follow the OpenMP standard will have to respect this required directive. Okay. And finally, some debugging tips. It's very easy to forget to map some data. So when you access it on the wrong device and you end up with your application crashes because the data is not allocated, or worse, your application does not crash, but is operating on some old data which has not been updated. For instance, because you forgot that map2 actually doesn't copy data if the data is on the device. So you're using a out-of-date copy. So your program will run, but the results will be wrong. Okay, so sometimes you want to see what the GPU is actually doing. So when debugging, it's useful to essentially tell the program to output information about what data is being mapped and being transferred. So this can typically be done by setting an environment variable. Now, this environment variable will depend on your compiler. So these are a few examples for some common compilers. So for Cray, which is what we have on ARCHER2, will be Cray AC debug, environment variable, NVIDIA NCARC notify, and for Clang and most compilers which are based on LLVM, which includes the AMD compiler, then it will be this libmp target underscore info environment variable. So the names are different and they print the output in different formats, but they all show you what's going on under the hood. So what data is being mapped to and from the GPU along with other information. Okay. So this is everything I wanted to cover today about how to copy and transfer data to and from the GPU. Anyone has any questions? Any further question? We had some question during the presentation, but if anyone has any burning question or random curiosity, okay. Will the course cover using OpenMP from GPU offload within MPI parallelized code? Unfortunately, no. So this is a single node course. I don't think we have any course where we actually cover using MPI. To some extent, it doesn't change much in the sense, typically what you do is that you assign, so for each MPI rank, you assign a different GPU. And then each rank offloads work to that GPU. It gets more complicated if you want to use multiple ranks with the same GPU. You can do it. It often doesn't work that well. And you have to do some exceptional, some things that will depend on your hardware, like MPS on NVIDIA. Don't think there's any equivalent for that on NVIDIA. But long story short, it's as long as you keep for each GPU, each rank uses one GPU, and use a version of MPI which is GPU aware, which means it will you can use it also with data which is on the GPU. There's not much of a change. But yeah, unfortunately, we don't cover that. No. Okay, sorry. Okay. If not, let's get back to the GitHub repository and go back to exercises. And so we have, so this is a more longer exercises, which is essentially solving for the Poisson equation, which is very common in many scientific domains. So you might have already come across it if you're doing any really physics-based simulations. So the first, the first, you can have a look at these instructions and essentially do the first part of exercise, the 3.1. And I will wait to do the following points because these use some more advanced techniques that we'll cover in the next session. So it's a bit more involved exercise. But the first part is essentially how to map data from the CPU to the GPU. So again, we will go. If you have questions, you can contact me. And in any case, we are going to cover, go over the exercises during our leave and do a leave demo at the end of the course. So that will be next week. Okay. That's, if there isn't anything else, I think we can close there and see you at the next sessions.